Hi there, I'm Michael Dembinski with MTS Systems, and today we're going to be going through some of the work we've been doing on virtual testing. With virtual testing, you'll essentially be able to test your system before it's even built. You'll be able to figure out your hydraulic flow requirements, your actuator sizing, your servo valve sizing, all before your rig is built while you're designing it. Before you can trust your virtual testing though, you need to go through validation efforts. So the demonstration we're going to be doing today, we're going to be running a virtual system and a real physical system all in parallel. Our physical system is going to be this bending beam right here. We have 4 actuators connected to the beam. We have a load cell, a servo valve, and a displacement sensor on each of the actuators, and it's going to be controlled from our controller over here. The controller is set up with a shared memory fiber optic network so that we can share data and signals with our target PC, which will be running the virtual test. To talk a little bit more about what we did with modeling and virtual testing, Shawn Gao will be speaking next.
Hello, my name is Shawn Gao, and today I will talk a little bit more on the modeling side. So in MTS, over the years, we have developed this proprietary model for our test systems. And these models have been validated over and over again on different systems. So they are all physics-based models, so you can change any parameters as you want, like tuning the controller gains and change to different valve size, different actuator size. So in this block diagram, I'm going to show you a little bit what we want to demonstrate today. So Mike already showed you the real physical system previously. So in the virtual test system, so we have the controller model, we have the servo valve and actuator model, and a lot of times our customer has their own customized test article. So our approach is that we start from a finite element model, then we convert it to a reduced order model. Therefore, we can integrate all those models together and run those in the real-time target PC. And therefore, that in real-time target PC can also interface with the controllers through the ScramNet shared memory, and we can then run them in parallel. And then now I'm going to sit down and show you something under the hood. So as you can see here, our models are all based on MATLAB and Simulink development environment. And from most outside, these are the input and output of the shared memory. And if we go into this block, it shows where our systems are modeled. And there are layers and layers of subsystem modeled here, so that we have a high fidelity model to capture all the physics in the real system. And now I'm ready to just build this model onto the target PC, and then we are ready to do the test.
All right, we have our test all set up and ready to go here. We also have a data display set up. The data display is set up with 4 plots, 1 plot representing each actuator on the bending beam. Each plot has 3 signals on it. We have a white signal to represent the command that is being sent to the real system and the virtual system. We have a green signal representing the actual feedback we're getting from the load cells themselves. We also have a red signal representing the feedback that we're getting from the virtual system. This is the load that we're predicting the load cells should be outputting during the test. Initially, we're going to be running just the virtual system because we have hydraulics turned off. And I think we're all set to go. Are you ready to go, Shawn?
Yes, absolutely. I will start the virtual test system right now. And now it's running.
Okay. And I'll kick off our test. Our test is going to be a square wave, just an alternating square wave going back and forth. And we'll adjust the tuning as we go. All right, and there our test begins to run. And as you can see, only the white signal and red signal are moving because we have hydraulics turned off, so we're not going to get any actual feedback at this time. And what we see here is the predicted feedback we should be getting once we do turn on hydraulics. So I think the next step is turn on hydraulics at this point?
Yeah, let's do it. Let's put on our safety glasses.
And go ahead and turn them on.
Yeah, as you can see, as the hydraulic kicks in, then the real system starts to respond as well.
Yep. I think we can change the tuning at all here, increase the P gain.
Okay, yeah, I'm going to change my virtual system tuning. We started at the peaking of 1 for all the actuators. Now I'm going to increase that to 3 for all of them. And it just changed. As you can see, this sudden change there is because my model changed the peaking.
Yep. And we can see now the green signal and red signal are starting to diverge. They're no longer matching. And that's because his tuning is now different than the tuning I have on the actual system. So I'm going to go ahead and update the actual system tuning to match the virtual system and see what happens. So P gain of 3 you said, right?
Yes.
All right, I'll kick that up in the real system.
Yeah.
And now you can see we have much better matching between our actual system and our virtual system. Do you think we can push it any more?
Yes, I think we can, and I'm actually going to go ahead and increase all the P gains to 5 in my virtual system now, and let's just see how the performance is. And we can see there are some kind of a high frequency oscillation there, meaning that the model is predicting that we are marginally at the border of instability.
Yeah, it's predicting that it should be stable though, so I should be safe to go ahead and put this into the real system. So I'll go ahead and update this to 5 as well. Yep, and it looks like we're getting much better matching here.
Yeah.
And we can also see in the green signal some
Wow.
vibration starting there, so we must really be on the edge of instability there.
Yeah, that's true.
Do you think we can go any further?
I think I can, at least, mine is a virtual system, it won't damage anything, so I'm actually going to go ahead and increase the P gain to 6 now, and let's see what's going to happen. Oh,
Wow.
that's not going to work.
Yeah, it looks unstable for sure. Do you think, should we try it on the real system?
Yeah, let's do it.
Okay, let's see what happens. So I'll go ahead and put it in on the next bang of the square wave.
Right, just be ready when you have to hit the stop if things goes unstable.
Yep, I'll be ready.
That's clearly
Clearly
unstable
unstable,
system. Of course, if it's a real test article, you will never do this to tune your P gain to such a high value. But our purpose today is to demonstrate that our model is able to predict the ultimate state like this.
Yeah, this is really just the tip of the iceberg. Not only will you be able to figure out the actuators that you need, the size of your servo valves, your hydraulic flow requirements, but you'll also be able to figure out your testing parameters. You'll be able to figure out your tuning parameters, your transition times, all before actually testing the real system. That's really the power of virtual testing.